Meteorologists can often recognize the potential for tornado outbreaks, hurricanes changing direction, and major snowstorms days before they happen. One of the biggest reasons is a map that most people have never even heard of, the 500 millibar weather map. Today, I'm going to show you exactly how to read it. Welcome back. Today, we're going to learn how to read one of the most important weather maps meteorologists use every day, the 500 millibar map. Now, if you've ever opened one of these maps and thought, I have absolutely no idea what I'm looking at, don't worry, that's exactly why I made this video. By the end, you'll know how to spot the big weather patterns, understand where storms are most likely to develop, and have a simple 5-step method you can use every time you look at a 500 millibar map. We're not going to memorize a bunch of complicated terms. Instead, I'm going to show you what to look for, explain why it matters, and then we'll finish by looking at a few real weather events where all the pieces come together. So let's start with a simple question. What exactly is the 500 millibar level? The 500 millibar level is located about 18,000 feet above the ground. You don't need to remember the number. The important part is understanding why meteorologists care about it. Think of it like looking at traffic from a helicopter instead of standing on the road. From up high, it's much easier to see where everything is moving. That's exactly what this map does for the atmosphere. The winds at this level help guide weather systems, which is why you'll hear people call it the atmosphere steering level. On these maps, you'll mainly see two shapes, ridges and troughs. A ridge is where the pattern bends northward. That's usually where the weather is quieter and temperatures are a little warmer. A trough is where the pattern dips southward. That's often where you'll find colder air and a better chance for clouds, rain, or storms. So learning to recognize those two features is the first step to understanding almost every 500 millibar map. At first glance, this map looks like it's covered in randomly squiggly lines, but they're actually telling us a lot. These lines are called isohypses. That's just the technical name. The important thing is to remember what they're like contour lines on a topographic map. Instead of showing mountains and valleys on the ground, they show the shape of the atmosphere about 18,000 feet up. As you look across the map, notice how some of the lines are packed close together, while others are farther apart. When the lines are close together, the winds are usually stronger. However, when they're further apart, the winds are going to be generally weaker. So these lines are going to be making it easy to spot ridges, troughs, and their overall flow of the atmosphere. Once you learn to recognize these steps, reading a 500 millibar map will become much less intimidating. Whenever I open a 500 millibar map, I always look for the same four things. First, I find the ridges. These are the northward bulges in the pattern and usually point to warmer, more stable weather. Next, I look for the troughs. These southward dips often bring cooler air and where storms are more likely to develop. Then I check for any closed lows. These are easy to recognize because the lines form a complete circle, since they're cut off from the main flow. They can stick around for a while and keep the weather unsettled. And then finally I look for areas where the lines are packed tightly together. That's usually where the strongest winds are located, and it's often where the jet stream is found. If you can quickly find these four things, you've already done a big part of the forecast. Not every trough is the same size. Some are huge, stretching across a large part of the country. These are called long waves, and they control the overall weather pattern for several days. Inside those larger waves are smaller ripples called short waves. A simple way to think about this is the long wave set the stage, but the short wave will often steal the show. As a short wave moves through the atmosphere, it helps give the air an extra push forward. That can lead to more clouds, rain, and sometimes even severe thunderstorms if the other ingredients are already in place. So when you're looking at a 500 millibar map, don't stop after finding the big ridge or trough. Look for those smaller waves moving through the pattern, because they're often what turns an ordinary day into an active weather day. Now that we know how to find the larger and smaller waves in the atmosphere, let's talk about another clue meteorologists use to figure out where air is most likely to rise. So far, we've learned how to find the major features on a 500 millibar map, but knowing where the ridges and troughs are is only half the story. Next, we're going to talk about vorticity, one of the biggest clues meteorologists use to figure out where storms are most likely to strengthen. Now let's talk about one of the trickier concepts in meteorology, vorticity. Don't worry about the name too much, the idea is actually pretty simple. Think of vorticity as a way of measuring how the air is rotating or spinning. Now, spinning air by itself doesn't automatically mean bad weather. What really gets our attention is when that spinning air moves into a new area. Meteorologists call this positive vorticity advection, or PVA for short. So the simple version is if you imagine pushing a shopping cart, if you give it an extra shove, it speeds up. PVA is kind of like giving the atmosphere an extra shove. It encourages the air to rise, and rising air is one of the key ingredients for clouds and storms. On the map, you'll often find the strongest areas of vorticity around troughs and especially around smaller shortwaves moving through the flow. That doesn't guarantee storms, but it does tell us the atmosphere is becoming favorable for them. So when you hear meteorologists talk about PVA, just remember this: more spin moving into an area usually means a better chance for rising air. Now let's look at another feature that works together with vorticity to strengthen storms. You've probably heard of the jet stream before, but what exactly is it? The jet stream is simply a narrow ribbon of very fast moving winds high up in the atmosphere. It acts like a highway that helps steer weather systems across the country. Inside the jet stream are even faster pockets of wind called jet streaks. Think of driving on the interstate. Traffic might already be moving fast, but every now and then there's a stretch where cars are moving even faster. That's basically what a jet streak is. These faster sections can help air spread apart high in the atmosphere. When that happens, air from below rises to replace it. And remember what we have already learned. Rising air helps clouds grow and storms become stronger. On this diagram, you'll notice areas labeled divergence and convergence. You don't need to memorize every quadrant today. The main thing to remember is that some parts of a jet streak encourage rising air, while others do the opposite. When a jet streak lines up with a trough and a short wave, that's when the atmosphere can really start coming together for active weather. So now we've learned two important pieces of the puzzle: vorticity and jet streaks. Next, let's compare what a quiet weather pattern looks like versus one that's ready to produce severe storms. Let's put everything we've learned together. This map shows a much quieter weather pattern. Right away, notice the large ridge across part of the country. Under a ridge, air tends to sink, which usually leads to calmer weather, fewer clouds, and warmer temperatures. The flow across much of the map is fairly smooth. We don't see any strong shortwaves moving through, and there's no major jet streak nearby providing extra lift. Without those ingredients working together, the atmosphere doesn't have much reason to produce widespread storms. That doesn't mean it's impossible for a thunderstorm to pop up somewhere, especially during the summer. But from a large-scale point of view, this is a fairly stable weather pattern. This is actually a good reminder that meteorologists don't look for just one feature. We always ask, how many of the ingredients are coming together? Now let's compare that to a pattern that's almost the complete opposite. Now this is a much more active setup. Instead of a broad ridge, we have a deep trough moving across the plains. Notice how the trough is beginning to tilt from northwest to southeast. That's called the negative tilt, and it's often a sign that a storm system is strengthening. We also have a strong shortwave moving through the trough, along with positive vorticity advection, or PVA, helping encourage rising air. On top of that, strong southwest winds are carrying warm, moist air into the region, and finally, a jet streak is helping remove air from above, allowing even more air to rise from below. Individually, none of these features guarantee severe weather, but when they all happen at the same time, they create an atmosphere that's much more favorable for thunderstorms and tornadoes. This is why meteorologists always look at the whole picture instead of focusing on just one ingredient. So what happened after that upper air pattern moved across the region? This map shows the tornado tracks from that outbreak. Notice how the strongest tornadoes developed just ahead of the main trough where many of the ingredients we just talked about came together. There was plenty of lift from the upper atmosphere, warm and moist air near the surface, and strong winds throughout the atmosphere helping storms organize. This is a great example of why the 500 millibar map is so valuable. By itself, it can't tell us exactly where every tornado will happen, but it gives us a big picture view of where the atmosphere is becoming more favorable for severe weather. That's exactly why meteorologists start with maps like this before zooming in on smaller details. Now, let's move on to one of the most famous severe weather events in U.S. history and see how these same ideas played out during the 2011 super outbreak. Let's fast forward to one of the most significant severe weather outbreaks in U.S. history, April 27th, 2011. Before looking at what happened, let's look at the atmosphere that morning. Right away, notice a large trough stretching across the central United States. That's our first clue that the weather pattern is becoming more active. Inside that larger trough are several smaller short waves. Remember from earlier, those smaller waves often provide the extra lift that helps storms develop. Also notice the jet streak behind the trough. It's beginning to strengthen the overall weather system and help the trough become more organized. At this point, you probably wouldn't look at this map alone and say a historic tornado outbreak is definitely going to happen, but you would say that many of the ingredients are starting to come together. The atmosphere is loading the pieces onto the table, it just hasn't put the puzzle together yet. Now, let's compare that with the map just 12 hours later. This is one of my favorite examples because it shows how quickly the atmosphere can change. The trough has become much stronger and has taken on what's called a negative tilt. Instead of leaning from southwest to northeast, it's now leaning from northwest to southeast. Why does that matter? A negatively tilted trough is often a sign that a storm system is reaching its strongest stage. It usually means the atmosphere is becoming much better at producing rising air. The shortwave has also moved farther ahead of the trough, helping lift the atmosphere even more. The jet streak is now lined up in a way that provides even stronger support for storms. When you compare this map with the previous one, it's easy to see the atmosphere becoming more organized. That's one of the biggest reasons meteorologists compare maps over time instead of looking at just one snapshot. Let's stop here for a second and look at everything that's happening at once. We have a deep trough, a strong shortwave moving through it, positive vorticity advection helping increase rising air, a powerful jet streak, strong southwest winds bring warm, humid air northward. None of those things by themselves guarantee severe weather, but when they all overlap in the same area, the atmosphere becomes much more favorable for strong thunderstorms. That's really the biggest lesson from this entire presentation. Forecasting isn't about finding one magic feature. It's about seeing how multiple ingredients come together at the same time. The more pieces that line up, the more confident meteorologists become that something significant could happen. Of course, all of those upper air features eventually showed up at the surface. The April 27, 2011 super outbreak produced hundreds of tornadoes across the southeast, including many strong and violent tornadoes. The important thing to understand is that these tornadoes didn't happen because of just one trough or one jet streak. They happened because the atmosphere had almost every major ingredient working together. The 500 millibar map helped meteorologists recognize this was an unusually favorable setup well before the storms reached their peak intensity. That's why upper air forecasting is so valuable. It helps us understand why an event is becoming dangerous, not just where the storms happen. So far, we've focused mostly on thunderstorms and tornadoes, but the 500 millibar map isn't just useful for severe weather. It also helps explain why hurricanes sometimes take unusual paths. Hurricane Sandy is a perfect example. Normally, hurricanes along the East Coast curve back out over the Atlantic, but Sandy didn't. A strong ridge of high pressure blocked its path to the east, almost like putting up a wall. At the same time, a large trough approached from the west and helped pull the storm back toward the coastline. The hurricane wasn't making that turn on its own. It was being steered by the larger weather pattern high up in the atmosphere. This is another great reminder that storms don't move randomly. Whether it's a thunderstorm, a winter storm, or even a hurricane, the flow at 500 millibars often tells us where it's likely to go. So far, we've looked at severe weather and hurricanes. To wrap everything up, let's look at one more example, a major winter storm. And then I'll show you the simple 5-step process you can use every time you open a 500 millibar weather map. Let's finish with one more type of weather, a major winter storm. Even though snowstorms are very different from tornadoes or hurricanes, the atmosphere still follows many of the same rules. On this map, you can see a strong trough moving across the western United States. As it moves east, it helps strengthen a surface low while pulling cold air into the system. At the same time, the jet stream is helping support rising air over the developing storm. That rising air allows moisture to cool, condense, and eventually fall as snow. Once again, notice that we're not looking at just one feature. It's the trough, the jet stream, and the overall upper air pattern all working together. Whether it's rain, snow, or severe thunderstorms, the process starts with understanding what's happening higher up in the atmosphere. By now, we've covered a lot, so let's put everything together into one simple process that you can use every time you open a 500 millibar map. Step 1. We want to find the ridges and troughs. This tells you where the main weather pattern is located. For the step 2, we want to look for any short waves moving through those troughs. Those smaller disturbances often help trigger active weather. Step 3, we want to find the jet stream and any jet streaks. Stronger winds high in the atmosphere can help storms organize and strengthen. Step 4, look for areas where several ingredients overlap. That's usually where the atmosphere is becoming more favorable for rising air. And finally, step 5, we want to compare what you're seeing with the surface weather. Does the upper air pattern match where the storms are developing? The more you practice these 5 steps, the faster reading these maps become. So let's wrap everything up. The 500 millibar map is one of the best tools meteorologists have because it shows the bigger picture. It helps us understand where weather systems are going, where the atmosphere is becoming more active, and why storms sometimes strengthen why others don't. Today, we learned how to identify ridges and troughs, how to spot long waves and short waves, why vorticity and jet streaks matter, and how all those pieces came together during real events like the 2011 super outbreak, Hurricane Sandy, and the January 2016 blizzard. Most importantly, you now have a simple 5-step method you can use the next time you open a 500 millibar map. If this is your first time learning about upper air forecasting, don't worry if you don't remember everything. Even experienced meteorologists continue learning every day. In fact, I have another video on this that's kind of more of an introduction on the 500 millibar one that I'll link in this video that you could view too as well to give you a more general understanding. This is a more in-depth understanding. But the important part is understanding the process. The more maps that you look at, the easier it becomes to recognize these patterns. And before long, you'll start seeing the atmosphere the same way professional forecasters do. Anyways, thanks so much for watching. If you found this video helpful, consider leaving a like, subscribing for more weather education and forecast discussions, and let me know in the comments what weather topic you'd like to learn about next. I'll see you in the next one.